Thank you, Christina, for the introduction, and thank you for having me here. I'm, as you said, Christina, I'm Luca Breseghello. I'm a PhD candidate at CREATE at the University of Southern Denmark. And today I will speak about stress-based design for 3D concrete printed horizontal structures. And CREATE is a research center led by Professor Roberto Naboni, working within computational design and robotic fabrication. And our research interest in 3D concrete printing lies in the premise that concrete is, with over 4 megatons a year, the most used material on Earth, just after water. And that in turn, the cement industry causes 7 to 8% of global emissions, with over 1.5 billion tons of CO2 emitted every year. So if we keep doing business as usual, emissions generated by the cement and concrete industry will grow proportionally to the projected growth in population and urbanization. So to reach net zero emissions, a combined effort by all stakeholders is necessary. And of course, a large portion of these emissions should be reduced by rethinking cement composition and its modes of production. However, it is also estimated that over 25% of today's emissions can be cut down through efficiency in design and construction. So finding new ways for carbon efficient design and construction means also rethinking the linear workflow that goes from design to engineering and to construction. And 3D printing, of course, brings geometric freedom and allows to place material only where needed. However, for an efficient material and carbon design and construction using 3D printing, we must consider the tight interdependencies between geometry, material, and fabrication. So our work goes in the direction of developing an integrated workflow that is able to account for these different aspects and integrate and exploit the possibilities given by 3D concrete printing. And our research was pushed forward through experimental work and the realization of a series of incremental structural prototypes of horizontal elements divided in 2 projects. Prior to that, we ran some preliminary process research, and parallelly to the experiments and through the experiments, we also developed digital tools and run fabrication and material tests. So the first phase of our research was to run investigations to achieve a high control over the process, both on the material and on the digital side. All the tests and prototypes were performed mixing a cement-based mortar with admixtures, polypropylene fibers, mainly for cracking, and integrating steel rebars in the structural elements. And all these tests were performed in a robotic setup, which in its final form includes a medium payload industrial robot and a continuous feed mixing pump and a connected silo. And this allowed us to print multiple structural elements in the same printing day with sizes reaching up to 3.6 meters by 2 meters. And this is how the setup at CREATE Lab looks after printing, so after cleaning up. And in a material perspective, looking at the material performance, we ran 3 different preliminary tests. And firstly, we looked at the compressive strength development of the used mix to understand both the early age behavior but also the stabilization phase and the characteristic strength of the material we were printing with. But a second test series investigated the influence of the anisotropy that characterize 3D concrete printing and 3D printing more in general. So we extracted extracted cylinders in different directions from printed specimens, and we tested them in compression. So the results are highlighting that there is, in fact, an isotropic behavior in the printed concrete, and that the higher performance is achieved when the specimens are loaded along the layers in the X direction. The third test series was running pull-out tests, so to evaluate the rebar concrete adhesion and the tensile strength in the different printing directions. And besides the Z specimens, so where we casted material and we put the rebar in cast material, the best performing printing direction was the one where we embedded the rebar along the printed layer. So parallelly to material tests, we worked on developing a digital setup, so to be able to design and preview our printed objects. So firstly, with the goal of achieving a high resolution control, we looked into how filament width and height could be controlled by changing the motion speed of the robot. And more specifically, we printed and evaluated a matrix of specimens with different layer heights and printing speeds. And from these, we measured the resulting width and as well as the quality of the print. So this provided us with a model we could use to set printing speeds and obtain target filament widths at given heights. So this model was then translated into a digital tool that could provide us with a quick yet reliable preview of the printed object. And parallelly also